Good morning, everyone, and thank you for joining me today for my talk on how we can use microseismic data in a reservoir simulation workflow to estimate production and drainage volume from multiple stacked wells. My name is Hassan Shojai, and I'm a reservoir engineer at Microseismic Inc. I will begin by briefly reviewing the traditional approach that is commonly used for reservoir simulation of unconventional resources and describing the shortcomings of that approach. I will then discuss how we can use microseismic focal mechanism and moment magnitude to build more representative reservoir models. I will go through the workflow using a case study from the Permian Basin where we have 8 wells producing from 3 different formations. At the end, I'll provide a summary and wrap up my presentation. The traditional and still common approach to reservoir modeling of unconventional wells is to assume planar biving fractures that have uniform spacing, half length, and conductivity, as you can see here on the right. I think we all agree that due to variabilities in reservoir properties and the existence of natural fractures and fault, hydraulic fracturing results in a much more complex fracture network in the reservoir. Obviously, using an unrealistic representation of hydraulic and reactivated natural fractures in the reservoir model will lead to unrealistic estimates of drainage volume. Therefore, it is needed to come up with more realistic models. Microseismic is one of the very few, if not the only measurement that is able to capture the reservoir rock's response to hydraulic stimulation in 3D, especially when obtained using a surface array. Traditionally, microseismic data have been used to determine the overall fracture orientation, which is often identical to SH max direction, the overall geometry of microseismic cloud or SRV, assess the fracture complexity, and identify and hopefully prevent geohazards. Our objective here is to extract more value from microseismic data in order to build representative reservoir model. I'll explain how we can achieve this goal using a case study from the Midland Basin in Texas, where we have 8 wells completed in 3 different formations. Here on the right, you can see map view, depth view, and gun barrel view of all the 8 wells and the microseismic data that have been collected using a surface array. Well 1 is landed in formation A, well 2 to 4 are landed in formation B, while well 5 through 8 are landed in formation C. We are using a surface array with thousands of geophones here. When a part of the rock breaks, depending on how the rock broke, some of the geophones get pushed in one direction while others get pulled in the opposite direction. We can use this information to perform moment tensor inversion and obtain a robust focal mechanism and moment magnitude for individual microseismic events. Focal mechanism describes the strike, dip, and rake vector of the fracture, while moment magnitude correlates to the created fracture surface area. I'll explain how this information is used to construct a DFN and calculate permeability enhancement in the reservoir, all the way to estimating production and reservoir depletion using a reservoir simulation workflow. On this slide, you can see the DFN that we generated based on microseismic data, as I briefly explained in the previous slide. Of course, there is a lot more details on how we build the DFN, but I won't go through them here for the sake of time. As you can see, the resulting DFN captures the variations in fracture, geometry, and orientation along and away from the wellbore, which is the key for building a representative reservoir model. The next step is to account for the amount of proppant that has been pumped into each stage. We start from the stage center and fill the DFN away from the wellbore until all the injected proppant is accounted for. This gives a subset of the total DFN that is likely to be propped, as you can see here. In the next step, we put a geocellular grid around the DFN and calculate the permeability tensor in each cell based on the total number of fractures in that cell as well as their orientation and aperture. In the figures at the bottom, here you can see the resulting permeability distributions in map view for all three formations. This will be imported into a reservoir simulator along with other data. We had well logs and core data from a vertical pilot in the vicinity of the pad, as you can see on the left. Here the curves represent well logs while core data are shown with open diamonds. These information are used to generate a layer cake model. As you can see here on the right, each layer of the model has a different value of matrix permeability, porosity, fluid saturations, and reservoir pressure. We had three separate PVT test results as shown here, one for each formation, which we use to define the PVT model for all three reservoirs. In case you're not a reservoir engineer, a PVT model describes how reservoir fluid changes with a change in reservoir pressure. For example, it defines when the gas phase starts to come out of oil and how oil and gas viscosities change as the reservoir pressure drops. Relative permeability and rock compaction data were not available, which is the case nearly all the time, so we treated them as adjustable parameters during history matching. Again, if you are not familiar, relative permeability curves describe how oil, gas, and water flow relative to each other in the reservoir, while rock compaction curve characterizes how fracture conductivity reduces with a reduction in pore pressure, which is equivalent to an increase in confining pressure. We specified bottom hole pressure profiles and calculated oil, water, and gas rates for all the wells. CMG IMEX was used in our work, but any other reservoir simulator can be used too. The actual data are shown with open circles, while simulation results are presented with solid lines. I would like to emphasize that a single multiplier has been applied to the SRV of all the wells in order to arrive at a history match for all rates. In other words, all the wells were treated equally here, and still the quality of history match is really good for almost all the wells. Our purpose here is not to arrive at a perfect match for individual wells, but to obtain a model that is able to reproduce the overall production response using the least possible number of adjusted parameters. We used only one multiplier here and arrived at a very good match for almost all the wells. This gives us a robust model that we can use as a baseline to analyze the production response and, most importantly, to estimate reservoir depletion and evaluate and optimize wellbore spacing. The endpoint water relative permeability curve was adjusted to match water-oil ratio, and the resulting water rates are shown here and compared with actual data. I'll get back to the interpretation of the results in a little bit. The endpoint of gas relative permeability curve was adjusted to match gas-oil ratio, and again the results are showing here and compared with actual gas data. We did not modify the original PVT models, but one can do so to improve the history match for gas rates. Now, I'm showing the total liquid rates, or oil plus water rates here. The total liquid rate is a very good measure to evaluate and analyze simulation results when you have both oil and water flowing in the reservoir. The first observation here is that the well number 1 here on the top left corner is underperforming. The operator has believed for a long time that formation A has significantly different flow properties, and it is much harder for fluids to flow in formation A compared to formations B and C. If you remember, we used the same rel-perm function for all three formations, and the fact that well number 1 produces less fluids than what reservoir model predicts is seen by the operator as a confirmation of their theory. Another interesting observation is for wells number 5 and 6, shown here on the top right corner. These two wells are located next to each other in formation C. Well 5 is overproducing while well 6 is underproducing. Interestingly, it has been observed in the field that well number 6 suffered from scaling problem, which caused that well to underperform. Since these two wells are neighboring wells with connected drainage volumes, as you will see in next slides, well 5 probably stole from well 6 and therefore overproduced. Another very interesting observation is related to frac hits. I'm showing the analysis for well number 4 here. In the left-hand side figure, the arrows represent simultaneous and sudden changes in pump intake pressure, oil rate, and water rate, which may be indicative of frac hits. Interestingly, the first sudden and simultaneous change in pump intake pressure, oil rate, and water rate coincides with time interval when a neighboring well was being treated, which I have highlighted here with yellow color. On the right-hand side, we see that actual oil production is much lower than model calculation, and actual water production is much higher than model calculation over the same time period. This further confirms the frac hit from neighboring pad. Please note that frac hits were not accounted for in the model. Probably the most important takeaway from this study is obtained from depletion analysis using reservoir simulation results. Here I'm showing reservoir pressure information A, B, and C in map view, and also in cross-section view along this dashed line, 5 years into production. A key finding is that there is a depletion gap between wells information B and C here, and also between well 3 and 4 within formation B. Since there is not a good quality reservoir between formations B and C based on the well logs that I showed previously, it's not recommended to drill new wells in the undrained region between formations B and C. However, a new well can be drilled between wells 3 and 4 within formation B to extract the oil that would be left behind otherwise. To summarize, we used microseismic-derived permeability enhancement distribution in a reservoir simulation workflow to calculate oil, gas, and water production rates. The model was calibrated using nearly 6 months of production data, but of course, as more production data becomes available, we can always go back and further calibrate the model. Model results agreed with actual production data fairly accurately. Pressure depletion results were used to evaluate wellbore spacing. This information can be used to optimize the spacing among different wells. We also used the reservoir model as a baseline to analyze individual wells' production response. And with that, I would like to thank you all for subscribing to this presentation. I'm leaving my email address here. Please feel free to shoot me an email if you have any questions or comments. Please remember that we listen.